Hey everyone, welcome to This Explainer. Today, we're unpacking something absolutely fascinating: why traditional IT networking rules completely fall apart in tactical wireless environments. We're looking at a space where the laws of physics take over, and where a simple textbook networking decision can accidentally jam an entire operation. So, let's get right into it.
Okay, let's just do a quick system boot sequence. Here is our 5-part mission briefing for today's tactical network deep dive. First, the tactical mission hook. Second, 3 modes of delivery. Third, the wireless airtime problem. Fourth, advanced multicast forwarding. And finally, matching traffic to modes.
All right, kicking things off with part 1, the tactical mission hook.
Picture this scenario. A patrol vehicle drops behind a ridgeline. A medic needs to send one urgent message to one specific unit. Meanwhile, 3 different command posts are all trying to watch the exact same live drone feed. And at that very moment, a brand new radio joins the network, and the whole team needs to know it's there. You've got 3 completely different communication jobs, and they are all competing for the exact same RF airtime. If you try to route them all the exact same way, you're either going to waste incredibly precious radio bandwidth, or, even worse, you're going to lose the message right when it literally matters most.
Moving right along to Section 2, 3 modes of delivery.
So how do we handle this? We can conceptualize these delivery modes pretty simply. Think of Unicast as a direct phone call. It's a private conversation between one sender and one receiver. Multicast, on the other hand, is a targeted group chat, where only specific members actually get the message. And then broadcast? That's your universal loudspeaker. It goes to every single reachable node in the network segment, whether they care about the message or not. Now, in a wired office building, getting these wrong is basically a rounding error. But in a tactical mesh, it's a literal matter of operational survival.
When you're triaging packets, your automated decision tree should always be asking these sequential questions to figure out who actually needs the data. Does exactly one node need this? Route it Unicast. Does a known, defined group need this? Route it Multicast. Does every single node need it, or are the receivers completely unknown to you? Route it Broadcast.
And that brings us to this incredibly memorable operational mantra: Unicast for individual treatment, Multicast for common content, Broadcast for unknown or truly universal recipients. This absolutely must act as your core rule of thumb in a mobile ad hoc network, or MANET. But remember, this isn't some set it and forget it kind of rule. You have to constantly reevaluate this whenever your mission priority or your network topology changes.
Okay, Section 3, the wireless airtime problem.
Let's talk physics for a second. In a tactical mesh, almost every node is a half-duplex radio. What does that actually mean? Well, it means a node has to completely finish receiving a packet before it can turn around and retransmit it. It just cannot listen and talk on the same channel at the same instant. Because of this, every single extra redundant copy of a packet chews up shared, highly contested RF airtime that every other node desperately needs. Compound this with unseen, overlapping nodes transmitting at the exact same time, which we call the hidden node problem, and your signal collisions just absolutely skyrocket.
And man, this leads us to a massive headache when you try to force wired network reliability onto wireless multicast. We call it acknowledgment implosion. Imagine a sender transmits a multicast packet to 50 group members, and all 50 immediately fire back a "got it" acknowledgment at the exact same time. Those replies flood back and completely jam up the very channel the data just used. This is exactly why multicast and wireless systems often intentionally skips link layer acknowledgments. It means it lacks guaranteed reliability, but it saves the network from collapsing.
So, here's the harsh reality of it all. If you rely on redundant unicast streams just to send a shared video feed to 3 different command posts, you are multiplying your wasted airtime across every single shared relay hop. Capacity in a tactical mesh isn't that shiny gigabit speed printed on the hardware box. No way. It's the usable airtime along the actual path. You have to preserve it at all costs.
Let's dive into some solutions in Section 4, advanced multicast forwarding.
Enter RFC 6621. This is a standard from the Internet Engineering Task Force, known as Simplified Multicast Forwarding, or SMF. It was built specifically from the ground up for limited wireless mesh and mobile ad hoc network environments. And honestly, it proves that efficient flooding is sometimes a mathematically acceptable trade-off, as long as it's highly engineered.
So how does SMF actually work under the hood? It relies on 2 brilliant mechanics. First up, duplicate packet detection, or DPD. Since nodes in a mesh hear packets coming from all directions, DPD detects and drops duplicates instantly so they don't get endlessly re-relayed in a loop. Second, reduced relay sets.
Instead of every node acting as a repeater, the network calculates a minimal connected dominating set, which is really just a fancy graph theory way of saying that only a minimal optimal subset of relays actually retransmits the data. SMF reaches the whole network, but with just a fraction of the redundant noise.
But, and this is a pretty big but, there is a major gotcha here for network engineers. Multicast protocols heavily rely on things like IGMP or MLD to know who is actually listening to a group. If you don't have your network devices specifically configured for IGMP or MLD snooping, Layer 2 multicast traffic completely erases its own efficiency advantage. The network doesn't know where the listeners are, so it panics, and it floods that multicast traffic to every single node. It acts exactly like a broadcast storm. Not good.
All right, let's put this into practice. Section 5, matching traffic to modes.
Let's break this down by actual traffic types. Unicast should absolutely be your default for certainty. You use this when you need those explicit link layer acknowledgments. We're talking about sending tasking orders, authentication logins, pushing a config file to a single device, or using it as a selective repair fallback when a node misses a crucial piece of a broader multicast stream. One sender, one receiver, confirm delivery. Boom.
Next up, multicast. This is your total workhorse for shared, real-time operational awareness. This is for your live drone camera feeds, your push-to-talk voice groups, and your common operating picture updates. But here is the secret sauce. Your group membership state must strictly follow actual mission roles. Don't just dump every radio into one giant multicast group where you're effectively just broadcasting anyway. You need a specific group for the medics, a specific group for the command staff, and so on. Keep it tight.
And finally, broadcast. A well-disciplined tactical mesh treats broadcast strictly as a rate-limited control tool. It is not a lazy distribution default for routine data. You use broadcast for neighbor discovery, like a new node shouting, "Hey, I'm here," or for limited route discovery, and of course, universal drop-everything emergency alerts. Every broadcast forces every single node to wake up, process the packet, and burn airtime, so you want to keep these exceptionally rare.
If we compare the airtime cost of sending just one drone video feed to 5 command posts, the results are pretty stark. Unicast is the highest cost by far because it forces you to create 5 totally independent streams. Broadcast is super high because it forces every uninterested node to process data they don't even want. Multicast is the lowest and most efficient. But keep in mind the break-even point. Multicast is only worth using when the airtime savings from shared forwarding actually exceed the overhead of maintaining the group and recovering lost packets.
So, as we resolve our opening scenario, the medics unicast message, the command post multicast video, and the new radio's broadcast discovery, ask yourself this vital question. Is your tactical network configured for textbook theory, or is it built for tactical reality? You have to measure your network failures under realistic mobility conditions. I'm talking actual interference and weak links, not just some clean line-of-sight bench test in a lab. When the mission is literally on the line, does your network gracefully adapt or does it silently collapse under the weight of its own traffic? Let that dictate your design. Thanks so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you on the next one.